Hello, guys. We're gonna continue our discussion about logic gates. Okay. Uh, so we started this circuit last time. Okay, and we solved it in 4 different cases. Let's check here, and we found out that when 0, 0, when the input are just zeros, A and B, I mean, these two inputs, the output is 0. And then whenever one of the inputs is 5, then its corresponding diode will be on. On means there is a current flowing and it's forward. Okay. And the output will be 4.3. Okay. And of course, if both of the inputs are 5, then both diodes will be on forward and on with currents. And the output again will be 4.3. Okay, and we postpone, the what kind of application is this to this video, and here is the time now. But before I delve into the applications of such circuit, I just want to highlight 2 important observations for this circuit analysis. First, when VA is 0 and VB is 0, so we discovered that V output is 0 as well. Okay. Now the question, what was the situation of both diode A and diode B? Were they forward? Were they reverse? What exactly? So we can determine whether they are forward or reverse just by calculating the diode voltage. If you know the diode voltage, you can know for sure if it's forward or reverse. Okay. So let's do that. So I will just put this here. So VDA, the voltage drop of diode A equal to VA minus V out. VA is 0 and V out in that case is 0 as well. So it's equal to 0. And if you do the same for diode B, you will find that VDB in a similar way equal to 0 as well. So it's 0. It's not positive, so it's not forward, but it's not negative as well. So it's not reverse. So basically this diode is working in here. And this point, it belongs to, it's a transition point again. It belongs to reverse, it belongs to forward. But we don't care about naming. What we care is about, what is the voltage, what is the current. So we know at that point the current is 0, which was our situation, and also the voltage is 0. Okay, so that's why here everything is 0 in that circuit. The voltages are 0, the voltage drops are 0, the inputs are 0, the output is 0, and also the current, all the currents are 0. IL is equal to 0, and by turn IDA plus IDB will be equal to 0. So they will be as well equal to 0. Okay. The second observation is around this circuit is, it's regarding your homework. It's not that a big remark. Okay. But I just want to highlight, whenever you know the resistance value, in which here it's 1 kilo ohms, you can determine easily IL. So IL will be the output divided by the value of the current. So let's do this. For example, let's calculate the current here for number 4. So IL equal to V out or VR. V out here is equal to VR divided by R. So 4.3 over 1 kilo ohms. So this will be 4.3 milliamperes. Now the currents, IA, and so IDA plus IDB from KCL equal to IL. Equal to what? Equal to IL. Okay. So the two diodes are matched. So we have two matched diodes. Okay. So if you have two matched diodes with same voltage drop, same VD, then you will have same current. So because they are in parallel, okay, and so there is no preference for this branch over that branch, you know, or the opposite. So they are parallel, they have the same input, same voltage drop. Okay, so IL will be divided equally between IDA and IDB. So here, in that case, IL equal to to IDA or to IDB, because they are both the same. So in that case here, IDA equal to IDB equal to IL over 2, so 2.15 milliamperes. Okay, how about you know, a case like this, in which one of the branches is one of the diodes is off and the other one is on. So basically, for example, if diode A is forward or on and diode B is reverse or off, then basically IL will be equal to IDA, because for sure, whenever the diode is off, and we are not considering the breakdown here, if the breakdown is not mentioned, then it's assumed to be very, very, very high, and it's not probable that the diode, the reverse diode, will go into breakdown. So its current is 0. So if we assume that DA is on, DB is off, then IL will be equal to IDA, because IDB is 0. Okay. Now let's highlight the application of this circuit. So this is one of the, you know, one of the most important applications for diode circuits, okay, in digital logic. So if you guys study, you know, there is digital electronics or digital design, okay, so you know what I'm talking about. So there are circuits called logic circuits. So if you didn't study these two courses, I will just highlight for you what I want you to know, basically what's considered important for us in this course. So don't worry if you didn't study these two courses. So basically, digital logic circuits, or these logic circuits, are circuits that do logic. They are thinking like us, okay? But each circuit do one type of logic or one type of thinking, okay? So think of it as, think of this OR logic. I'm not talking about circuit now. This OR logic that this circuit is representing, the circuit that we just solved, okay, represent this way of thinking, okay? What is this way of thinking? Basically, if you have operation and you want to do this operation based on some conditions, okay? In our case here, the circuit has two inputs. So our operation has two conditions, okay? Condition A and condition B. So you will not do that operation until at least one of the conditions is satisfied or true in logic, you know, in logic language, we can say. So we represent satisfied as 0, I'm sorry, as 1 or high or 5 or high voltage, okay? And we represent false or not satisfied or, you know, as low or 0, low voltage, I mean, or 0, okay, as a symbol. Or so basically, when we enter 0, when the input is 0, VA or VB, that means this condition is not satisfied, it's false, it's not true. And when we input 5 to either A or B, the voltage A or voltage B, then we are saying that the condition is satisfied or true, okay? And in that particular logic thinking, okay, the logic here is to do the operation if at least one of the conditions, at least maybe two or just one of them, is satisfied, is high, is true. High voltage, 5. Okay? And that's, we can represent, so these are the circuit outputs and inputs. When we put 0 volt and 0 volt, we get 0 volt. When we put 0 volt and 5 volt, we get 4.3 volt. So these are all voltage values that we put to our circuit. But we can represent it in a more formal way, you know, in such way here. So we represent false or low voltage with L, low. L for low, which represent 0 voltage. Or low voltage in general. It might not be 0, but low voltage in general. And we represent, so in that case, low and low, false and false, both conditions are not satisfied, so we will not do the operation. False. Here, low and high. High means high voltage, like 5 volt. But again, 5 volt, one of the options. Maybe you see other circuits with a voltage that is considered high, but not 5, 6, for example, or 4. Okay. So in that case here, one of them is satisfied, so we can do the operation. Here, one of them is also satisfied, so we can do the operation. Here, both of them are satisfied, so we can do the operation as well. Only the first case, in which we have low and low, we cannot do the operation. Okay, one example here is a vending machine, okay, that accept cash or card. This is all logic, and it can be done using our circuit. Okay, so when the user puts cash, okay, good, we have money in a form of cash. Okay, if we put credit card, that's also good. Okay. If we put both, I mean, the guy wanna pay cash, but he's not sure, you know, how much he should pay. He put the cash, he put also the card, okay? Then the machine will choose one of them. That's also okay. Okay. So that's basically, you know, one, of course, you can think of hundreds or thousands of applications of this. So digital computers, the computers that you are using every day, your laptop, okay, is full of such OR gate. Okay, but maybe it's not implemented with this circuit that we just discussed. I mean this circuit here, because this one form of circuits that can do OR, you can do it with many others. So, I mean, this is one of the circuits. So the OR logic is constant, but can be implemented with different circuits. This is one candidate of the circuits that can do OR logic for you based on the diodes. It's very simple, as you see. Okay. Another logic, which will be your assignment, is the AND gate. So the one that we discussed is OR gate. Okay, the circuit in front of you now is called AND gate or AND gate circuit or digital AND gate logic circuit. So here, this AND thinking means AND. I mean, you have again some operation, and you will perform this operation based on some conditions, and the condition to operate or do such operation is that all the conditions must be satisfied. So this is what represents the AND logic for two conditions. So here, if both conditions are not satisfied, you will not do the operation. If one of the conditions is satisfied, this is not enough, so we will not do the operation. Again, one of them is satisfied, but that's not enough for our operation. Okay, here two Both of them are satisfied. So we can do the operation. Or at least one of them. Here, they must be both. Both are satisfied. Just think of it as your air condition. If you have a smart home, a smart air condition, okay, it's warm, for example, not it's at winter, of course, and maybe the temperature is you want to set the temperature, for example, to 65. Okay, good. If your air conditioner is smart, okay, he should check two conditions, not just one. The conditions that just came in your mind is that, okay, if the temperature is higher than 65, then turn on the AC and try to lower this temperature to 65. That's good. But how about if your home is empty? I mean, there is no one in your home right now. You are in your work. If you have a wife, is also in your work. Your kids at school, and there is nobody in your home. And the temperature now is 68 or 69 or 70 or whatever. No, but there is no value to turn on the AC. Nobody will benefit from this. You will just pay money, a cost for this electricity with no value because nobody was there in your home. Okay, so there are two conditions here. So the air conditioner must check the temperature if it is higher than 65, and at least one of you guys is at home. So if both conditions are satisfied, then turn on the AC and try to lower the temperature to 65. If you are at home and the temperature is below 65 already, so why to turn on the AC? The weather is already good. If nobody at home, but the temperature is higher than the AC, again, one of the conditions is satisfied, but again, no value to turning on the AC. Okay, so somebody should be at home. The temperature must be higher than 65 to turn on the AC. So this is a kind of operation, that needs two conditions, and both of them must be satisfied in order to perform the operation. Okay. Now, what we care about here is to solve the circuit. Okay, this is your homework. But I will do one of the cases with you. So you must do 4 cases. You must do 0, 0. You must do 0, 5, 5, 0, 5, 5. I will do with you, for example, this one. VA 0, VB is 5. Okay? So let's do that. So VA 0, VB is 5. Let's go back to here to the circuit to check. So I will put here 0. I will put here 5. When I say put 0, that means I just connected this point to ground. When I say I put here 5 at VB, that means I could just connect a battery here with 5 volt. Okay. Now let's check. Remember here, the circuit is different, of course, from the other circuit. These two guys here are switched phases. I mean, the N side is toward the inputs and B side is towards the rest of the circuit, opposite to what we have in the OR. Let's check the OR so look at the OR here. They are opposite sides. Okay, and we have also here a 5 volt battery. This can be drawn, and you will find it. If you search for it on Google, you will find it drawn as in such a way. VA, VB, and nobody will draw a battery here. They will just put 5. So this node here is 5 volt. But what does this mean? Basically, we connect it to a battery of 5 volt. That's what it means, to put a node with some value for voltage. Anyways, so let's go back to our solution here. So we put here 0 at VA, we put 0 at VB. Now, let's guess. Yeah, everything is based on assumptions. Let's guess now. Are they on or forward with voltage higher than 0.7, or they are reverse or off? Let's guess. So let's start by DA. DA, which has input 0, okay? Now let's check its N side and the B side. So its N side is connected to the minimum voltage in the circuit. So look at this circuit. This circuit has two types of voltages, ground or 5 volt. So the highest possible value for the voltage is 5, and the lowest or the minimum possible value for the voltage is 0, ground. And the N side of A is connected to ground. So possibly, and the B side is closer to the 5. So possibly DA will be on. It's assume. Again, assume. Now let's check DB. DB, its N is connected directly to the 5 volt, the highest voltage in the circuit. The highest voltage in the circuit. And its B is close to this 5 volt. Again, the highest voltage in the circuit. And remember, for our diode under constant voltage model to operate, its B should be higher than its N by 0.7. Its N now is connected to the highest voltage, 5. It's 5. Vn I mean the terminal, the N terminal of DA is 5 volt. Or I'm sorry, of VB is 5 volt. So for sure, the other terminal will be less than or equal to 5. So basically, VB will be less than or equal to Vn of diode B. So it's probably, I for sure, for me, I know, for sure it will be reverse. It will be off. So DB is off. Again, if you just messed up, we assume, my friend. So we assume something, then we prove or disprove. And I will do, the bad things, I mean the incorrect assumptions with you after we finish this. Okay? So, but this is the correct assumption. So let's continue with this. So if we assume the A is on, then VDA is 0.7. So the voltage across A is 0.7 in that direction. And VDA is equal to VO, or this point, minus this point. VO minus VB. This point is VO, and this point is, I'm sorry, VA. This is VA. This point is VO, this point is VA. VO is unknown for us till this moment, and VA is known. This is the input, and it's 0 right now. So from this, we can say that VO equal to how much? VO minus 0, 0.7. 0.7. So here, this guy is 0.7. Now let's check VB. So we remember DB is off. So it might be reverse, it might be forward, but with voltage less than 0.7. So let's check that. So let's determine VDB. VDB is unknown. VDB is the voltage of that guy equal to that point minus this point. This point is VO, which is known now. And this point is VB. And it's known because it's 5 volts. So VO is 0.7, VB is 5. It is minus 4.3 volts. It's minus. So it's reverse. So that means diode B is reverse. And this is, compatible with our assumption. Remember, we assume that dB is off. dB is off means the diode is either reverse or forward, but with a voltage less than 0.7. Okay, that's good. Now let's continue and determine the currents. I is the current flowing in that branch here, in that way. Why I assumed it's in that way? Basically because you have here a source of 5 volts. So basically, and this is the highest voltage in the circuit. So the current should go out of the battery, okay? But if you have two batteries in your circuit, one of them is higher than the other, the one with lower voltage, it might be charging something. I mean, it has current flowing out of its positive terminal, or this or it's been charging by other source. So at that case, the current in this case the current will be going into its positive terminal. If you have two sources, if you have two batteries in your circuit, okay. Good. So let's continue here. Let's determine the currents. So I is equal to this point minus this point divided by the value of the resistors. So I equal to, again, this point is 5 minus this point, which is VO, which is 0.7 over R, which is 1 kilo ohm. So 5 minus 0.7 over 1 kilo. This is 4.3 milliamperes. And I is equal to, let's go back here. So I will be branched into IB and IA. So I is equal to IA plus IB. So IB is, yes, this guy is off. So for sure, IB is equal to 0. So IB here is equal to 0. So from this, IA equal to I equal to 4.3 milliamperes. Look now, IA is positive and flowing in that direction. So we are all good. We checked with two checks. We have an assumption here that D is on, DB is off. And we have proved this with two checks. The first one we found really that DB is reversed, so it's really off. And we found that the current through A is positive and flowing from B to N. Okay, and it was forward on in the beginning, so in our assumption, so it's really correct as well. Okay, so how about if we are, you assume I am stupid, I'm not, smart, and I didn't get all such ideas when I first assumed that DE is on and DB is off. I really doubt that DB is off. It may be on. Okay, so let's assume that both are on. Let's assume so. Let's assume that both are on. So let's do that with. So we finished now this case. I mean, what I will do now is just a check. Okay, and in that case here, which is VA is low and VB is high, we get the output here is equal to 0.7. And now compare, just before I continue, just to compare this 0.7 with 5. Is it so if this is 0, which considered low voltage, and this is 5 here, which considered high voltage, and here is the 0.7. The 0.7 is closer to 0 or closer to 5. It's for sure closer to 0 than 5. That's why it's considered low as well. And in our cases here, this is good to mention. Again, we have 0, we have 5. This is considered low, this is considered high. And in the OR circuit, the output was 4.3, which is closer to 5 than the 0. So it's considered high as well. So in digital circuits, you will have two groups, not two voltages, two groups. Group of voltages that considered high. They are very close to each other, and all of them is very close to the maximum high voltage, let's say, which is the battery voltage usually, which is 5 in that case. and you will have a group of voltages that are very close to the minimum voltage in the circuit. In that case, the zero, the ground. Okay. So let's go back here. Now let's assume, I said we just finished this case. We just finished it, but let's assume just for the sake of, you know, to be more sure, that dB is off. I'm sorry, dA is off, or any other combination. Okay. So on a side here, assume that, let's do dA on and dB on as well. Although that's wrong, but let's assume that. So if dA is on, then VDA equal to 0.7 equal to what? Equal to, let's check VDA. Yeah, VO minus VA. VO minus VA. VO is unknown. VA is known, which is the input, and the input here, VA is 0. So from that, VO is equal to 0.7. Okay, that's fine. Now VO is known, right? Okay. Remember, you assumed that dB is on. dB is on. So its voltage must be 0.7, right? So let's do that. So VDB equal to, let's check what is VDB equal to. VDB is equal to VO minus VB. VO minus VB. And remember, you said that dB is on. VO now is 0.7. And VB is 5. So VDB, the voltage on diode B, the voltage drop on diode B, is minus 4.3 volt. Negative. So you assume the diode B is on, which means it's in forward bias. Let's check here. You assumed it's forward and on. So its VD should be 0.7. It should be positive and equal to 0.7. What you get here, that VDB is minus 4.3. It's contradicting with the assumption that VDB is on. So this contradicts that diode B is on. You might think in the solution in another way. Let's do it. So if you didn't do that, you can still prove that this assumption isn't correct in that way. So in here, we started by VDA is equal to 0.7. So let's do that VDB is equal to 0.7 as well. VDB is equal to VO minus VB. Let's assume that we didn't still know VO, how much is VO. So from here, VO will be equal to 0.7 plus VB. VB is 5, so this will be 5.7. How come? How come you have the highest possible voltage in a circuit, which is the sources, so 5 volt, and you have a voltage that is higher than the maximum possible voltage? This is higher than the maximum possible voltage in the circuit, which is the battery 5 volt. If you have a circuit with a battery, you cannot find a voltage drop in that circuit higher than the battery voltage. You will have some discrepancy. What is this discrepancy exactly? Just look at I. I is flowing, must be flowing from that battery to this point. I mean, this point should have a higher voltage than this point. Okay? So if we consider VO is 5.7, then I will be 5 minus 5.7 over R. It will be minus 0.7 amperes or milliamperes, which is wrong. You cannot have a battery that you know, it charged, which been charged by another source. You may say the input is 5 is a source. Yeah, but this source has same voltage as our battery. So if you have two sources with the same voltage, they cannot charge or this, in each other. You know, one of them can charge the other. Another discrepancy here, which is really obvious, okay, and maybe better than or more understandable for you than all of this, that we have two equations, this equation and this equation, and both give us, you know, different VO. From here, VO is 0.7. From here, VO is 5.7. Which one we should consider, right? You cannot have a node in your circuit with two voltages. Must have only one of them, either 0.7 or 5.7. Okay, so that's basically how you think in some assumptions. So you, again, if you just wanna, you know, waste your time, but eventually when you will get the right answer, you can just go in a brute force manner that you assume all the conditions on off, off on, off off. They are 4 because you have two possibilities, right? You can do that, and you will prove that just by looking at the numbers that you get, that only one of them is correct. Okay, guys. So this is basically one possible applications for the diode in logic circuits. Okay, we explored in details, very high details, the OR gate. Also here the AND gate. I just give you the, you know, the a very good start, maybe halfway to do your homework, which will be to complete the table and asking for the current and stuff. Okay, so keep tuned for or stay tuned for next videos. We're gonna continue our diode circuit analysis. We have still very good examples to explore. So thank you very much and have a good day.